In this SV code, we are implementing a synchronous FIFO. FIFO is a memory structure where the first data written into the FIFO is the first data that comes out. It is widely used in digital design to transfer data between different modules while maintaining the order of data. Here, module declaration. We start with module declaration. Here, depth 16 means the FIFO can store up to 16 entries, and data with 8 means each entry is 8 bits wide. Using parameters, we makes the design reusable because we can easily change the FIFO size without modifying the internal logic. Here we have input ports and output ports. Here the FIFO has several inputs and outputs. Clock is the clock signal, reset is reset signal. Here write enable signal is used to write the data into the FIFO. Read enable signal used to read data from the FIFO. Data in is the input data bus. We have output signals or data out full empty. Data out, which provides the data being read. Full indicates that the FIFO cannot accept more data. Empty indicates that no data is available to read. Here, reach data with -1 down to 0, mem of 0 down to depth -1. Here, this line creates the FIFO storage memory. Since data width is 8 and depth is 16, we have an array of 16 locations, each capable of storing 8 bits. Here, reach $clock to of depth -1 down to 0 right pointer. Here the right pointer keeps track of where the next data incoming data should be stored. Same read pointer. The read pointer keeps the track where the next data should be read from. For a depth of 16, we need 4 bits to address all memory locations, which is automatically calculated using $clock 2 of depth. Reach $clock 2 of depth down to 0 of count. Here the count register keeps track of how many entries are currently stored in the FIFO. Count creates increase during write operation, decrease during read operation. Count remains unchanged when read and write happens simultaneously. Here reset, when reset is active, all memory locations are declared. Write pointer, read pointer, reset to 0, count becomes to 0, output data becomes to 0. This case occurs when write is enabled and read is not enabled. Here it stores incoming data into memory at the current write pointer location. Increments the write pointer, increments the count value. This means one new item has been added into the FIFO. It is when 2 in binary value is 2. When binary value is 1, read operation will happen. Here in this case it occurs when read is enabled and write is not enabled. Here the read data from the current read pointer location places it on data out. Here increments the read pointer, decrements the count. This means one item has been removed from the FIFO. 2-B11 here in binary value it is 3. Here in this case occurs when both write and read are enabled at the same clock cycle. The FIFO writes new data into the write location, read existing data from the read location, increments both pointers. Notice that count is not changed because one data is added from one data is removed at the same time. Now ideal condition like it is default. If neither read nor write is requested, the FIFO remains ideal and retain all existing values. Full flag logic. Here assign full count equal to depth. Here when the count reaches the FIFO depth, all locations are copied and the FIFO becomes full. The full signal prevents additional write operation. Count equal to 0. When count becomes 0, there is no valid data available in the FIFO. Empty signal prevents read operations. No errors.